Guys, welcome to another lecture from ecopoint. In the previous class, I discussed the concept of linear combination with you guys. Today, I want to talk about the length of a vector. Length of any vector, this concept is associated to distance. So before we talk about what is length of a vector, let's talk about distance between 2 points in Rn. So if you have 2 points, say Q, let's take a simple case of R2. So say Q is the point Q1, Q2, and P is the point P1, P2. So suppose Q is here and P is located here, the vector. Well, we are interested in the distance between Q and P, T, Q, P. This distance is nothing but, in order to understand the distance between P and Q, what you can do is you can just extend this figure as this right angle triangle. If you observe now, your distance between PQ is nothing but the length of the hypotenuse, right? Isn't it? It's the length of the hypotenuse. And what is this length and this length? By the Pythagorean theorem, we can easily figure out that distance between PQ is nothing but, it's the square root of the squares of the length, this and this length in this right angle triangle, okay? In other words, if you observe, what is this length, what is this length? This is your x-axis, this is your y-axis. So this is the absolute difference between P1 minus Q1 and the square of that. And similarly, for the y-axis, it will be P2 minus Q2 absolute value and the square of that, which gives you that this is nothing but square root of P1 minus Q1 square plus P2 minus Q2 square. I'm sure you can recall this is nothing but the distance formula. That's how you get the distance formula. Now, if you change the dimension from R to 2, you start thinking in terms of R3. In R3, there will be Q and P. Q would be a 3-tuple Q1, Q2, Q3. P will be again a 3-tuple P1, P2, P3. And you would observe that the distance formula would just get extended. Your distance between QP would turn into the square root of P1 minus Q1 square plus P2 minus Q2 square plus P3 minus Q3 square. Okay? And so on and so forth. Now, clearly that means we can conclude that distance between points could be defined as the following. Let P be an n-tuple, P1, P2, Pn. So let's take points in Rn. And Q is again an n-tuple, Q1, Q2 till Qn. There are 2 points in Rn. The distance between these 2 points could be defined as dpq and could be given as P1 minus Q1 square plus P2 minus Q2 square plus so on and so forth. Since we had n tuples, so Pn minus Qn whole square. This is the distance formula. It could also be written like symbolically, it could be written like this. Okay. Now, why are we talking about the distance formula at all? Because length of vector comes in from here. Recall pictorially when we define a vector, we say that, vector u is, say, something like this. This could be in R2, in R3, wherever. It has a direction and it has a magnitude, okay? And whenever we start the vector, where is the tail starting from? So you always have its tail at a point which is the origin. It could be 0, 0, 0, 0, 0, whatever is your origin. So tail of the vector is the origin. And therefore, when you define length of a vector, you define the length as a distance between the origin and the vector. So therefore, formally, let U be an n-tuple U1, U2, Un, the way we define a column vector or a vector, be a vector in Rn, the length of U given by, look at this. This is the symbol for length. Length is also called norm or magnitude. Given by this is the formula u1 square plus u2 square plus so on and so forth till un squared, the square root of that. Now, how come it is u1 square plus u2 square plus so on and so forth till un square? Basically, this is nothing but it is the square root of u1 minus 0 square. Since you are taking the distance between this is one n-tuple and the other n-tuple is 0, the origin. So, it is basically the square root of u1 minus 0 square plus u2 minus 0 square, so on and so forth till un minus 0 square. That's what is norm for any vector or length of a vector. Okay? Now, there is a very famous terminology, and that's unit vector. Now, what is a unit vector? It's a vector whose norm is 1. Or in other words, unit vector is a vector with length equal to 1. So, U is a unit vector in case the norm of U is 1. Now, there are some properties associated to length of a vector. When you are trying to understand these properties, remember that it's distance, okay? So, point number 1, the length of any vector has to be greater than or equal to 0. Number 1, it is distance. It has to be positive. Number 2, it's a square root. It will definitely be positive. Number 2, second property, in case the length of any vector is 0, when is that possible? It's only possible when we are talking about the 0 vector, or we're basically talking about the origin. So length of a vector is 0 if and only if that vector itself is the 0 vector or origin. Third property, if you try to take the length of k times, where k is any scalar, you take k times u and you try to find the length of that. That will always be equal to the absolute value of k into the norm of u. Why absolute value? Because norm cannot be negative. K could be negative, but when you will take k out of the square root, just take an example. Suppose we are in R2. So the length of ku means that I have ku1 square plus ku2 square. Now, of course, k could be negative. We are not saying that k has to be positive. So what happens is k square could come out common, and then you have u1 square plus u2 square. So k can come out, but outside the square root. Of course, just the positive one will come out, right? So absolute value of k multiplied by square root of u1 square plus u2 square, that is absolute value of k into the norm of u. That is why this third property. One additional thing I would like to discuss with you guys is the normalizing of a vector. What do you mean by normalizing a vector? We know what a unit vector is, right? A unit vector has norm equal to 1, right? You can always normalize a vector into a unit vector. How? Just imagine that you have a vector v. Let v be a vector, say in R2, and u be a unit vector in the same direction. Then do you know what u will be? We can define u as v upon the norm of v. Do you know why? Basically, v upon the norm of v, this new vector, will always be a unit vector. The reason, suppose we have already taken this case in R2. So this becomes pretty simple. Whatever is your vector, say v1, v2, the norm of v1, v2 will be v1 square plus v2 square. Now, if you take another vector, which is v upon the norm of v, this vector will become v1 upon square root of v1 square plus v2 square, v2 upon square root of v1 square plus v2 square. If you take the norm or the length of this vector, what do you think it will turn out to be? It's the square root of v1 upon square root of v1 square plus v2 square, the whole square of this, plus v2 upon the square root of v1 square plus v2 square, the whole square of that. Which means what I get is square root of v1 square upon v1 square plus v2 square plus v2 square upon v1 square plus v2 square, which means I have v1 square plus v2 square in the numerator, v1 square plus v2 square in the denominator, that is square root of 1, that is 1. So unit norm. So yes, this is what we mean by normalizing a vector. How do you normalize a vector? You take a new vector, which is the same vector v upon its norm. the norm of this new vector will always be 1. For example, if I take in R3 the vector 1 minus 3, 4, transpose of that because we take column as our vector. Okay, so the norm, this is your V, and the norm of V will be square root of 1 plus 9 plus 16. So this gives you square root of 26. If you now create a new vector V, which will be a new vector U in the same direction as V upon the norm of V, that vector will turn out to be 1 upon square root of 26 minus 3 upon square root of 26, 4 upon square root of 26. And if you now try to find the norm of this, it will be equal to 1. This is what is the concept of normalizing a vector. In the next class, we'll get a little deeper into vectors and we will talk about the dot product. Thank you very much.